Well, this is the second of 6 recordings on spectroscopic methods used for characterization of organic molecules in the undergraduate organic labs. So the first one covered really how the NMR works. I focused on mostly the little field from the sample that's aligned or opposed, not perfectly, but in 2 states by the big field of the instrument, and how a radio frequency impulse by the instrument causes the little field to flip or be affected, and we pick up that signal as it relaxes back. That's just a little. The video was just one of many that are available online that explain how NMR works. There are others that are very good that you may want to check out. But let's shift now to what do we know about the spectra in relationship to the structure. So yes, the black box, the NMR, we need to know how it works to some degree, but we also need to know the relationship between the spectra that it spits out and the structure that we put into that black box. How do we determine the structure given the spectra? Or if we know the structure, how can we predict what the spectra will look like? Well, we really have to unpack 3 things. We have to look at the number of signals and know that the maximum number of signals, or the number of signals, cannot be, more than the number of non-equivalent protons. If we were to have separation of all the signals and have no overlap, then the number of non-equivalent protons would equal the number of signals in the NMR. Integration, really just talking about the area under the curve. So I've just got these 2 curves here. And let's say this one was 3 times as big as this one. They're just singlets or whatever. We could say then for sure that given the area for one signal is 3 times that of the other signal, the number of non-equivalent protons represented in the same ratio. There are 3 times as many protons represented by this signal as there are represented by this signal. So integration is important. And in the next video, in the 3rd video, we'll be looking at integration and splitting. Let me just say at the outset for splitting, remember splitting of a signal is not due to the proton that generates that signal. It's always about the neighbors. Splitting is always about the neighboring protons. The proton that causes the signal, or is the source of the signal, is not the point of focus for splitting. Splitting, we look to the neighboring protons that are around the proton that gives a particular signal. Excuse me. So let's stop there in just a preview, and we'll of course have videos that cover C13, IR, and mass spec. Let's just unpack one box in this video, the second on proton NMR spectroscopy. Let's just unpack the box of, number of non-equivalent protons or number of signals and the position of those signals, the position where they fall in the spectra. And we're going to unpack, these 3 boxes of information, looking at structure and deducing or proposing a spectra that we would have given a particular structure. We need to know how to work the other way, and we'll do that at the end of these 6 videos. So here's my cartoon. Let's take a penguin and a cat. They are having fun with some molecule that they're hitting back and forth. But the penguin says to the cat before he hits this diethyl ether, this is an oxygen in red, and we have 2 carbons here, methylene and methyl group. So he's hitting it over, and he says, hey, check out the hydrogen on the end. So let's point to this one. Well, after tumbling and bumbling over the wall, we'll have a little wall here, so you can't try to keep track of it as it's, of course we can't in solution. These things are tumbling and bumbling even faster than our minds can even process as far as speeds. So when it comes over, the cat cannot know which exactly the penguin pointed to, but he can know for sure that it wasn't the 4 interior ones because of the description that the penguin gave, and because these are discernible, these 6 from these 4. Now again, these 3 are equivalent because we can spin real fast along this CC bond and your eye can't keep up, or we can spin along the plane of symmetry here. We could take a spinning of this structure, the whole structure, and stop it, and this side could be over here and this side could be over here, and you wouldn't know. So it can be wrong up to 5 times when the cat tries to pick the proton that was pointed to. But the cat can know for sure that the 4 interior protons were not pointed to. So we're going to start seeing then that this is important. The number of signals in a spectra equals or less than the number of non-equivalent protons. Now why do we have to put in that qualifier or less than or are less than? Because we can have some signals that overlap. They're for protons that are just so similar. They're not perfectly equivalent, but they're so similar that their signals just overlap. So we can't have fewer signals than the number of non-equivalent protons, but we can't have more signals than the number of non-equivalent protons. Let's look at those 4 on the inside. So we know there are 6 methyl protons on the outside that were truly equivalent. There's a little bit of a difference here with these 4 methylene protons. We know that they're not the 6, but their relationships to each other are a little bit different. These 2 here that are on the diagonal, we can truly say are equivalent. I can make this one sit exactly where this one sits by just twisting the structure. And of course I can do the same thing for these 2. So these would be pairs that are exactly equivalent. But really, if I were to hold on to the structure, I could say that I will never pick this one having picked this one here to the front. That would never happen, because I could reorient the structure so that I always have the oxygen down. Let's say this is always on my right, this group will be on my left, and I could possibly mistaken this one here for this one, but not this one. So these have a different relationship. They're called, and I'm going to use a term here and we'll explain it, just discuss briefly how you would observe these 2 as distinct from each other, but then move on, because typically we don't discern these as non-equivalent. We usually consider them as equivalent. These 2 are called enantiotopic protons, and let me explain what that means. If we take either of these 2 protons, either one, and replace it with something altogether different, we create a chirality center. So this carbon would be connected to an O, and let's say we leave one H on and we turn this into xenon or some element altogether different from everything else. So O, H, xenon, and a methyl group. Well, then that would be a chirality center. If we do the same thing from the other side, we would create the enantiomer by putting the xenon not here, but here we would create the enantiomer. So these are called enantiotopic protons. Now all that said, so let's just kind of point those out. I'm going to say A and B, A and B, and of course we can do it for these 2 also. They would be enantiotopic because we create a chirality center, and if we put the xenon here or whatever element, we create a chirality of one nature, but if we put it at A, it's the opposite nature. So these are called enantiotopic protons. All that said, we never really see them as distinct from each other or non-equivalent, because you have to use chiral solvents to see enantiotopic protons as giving different signals. Chiral deuterated solvents, typically seldom used in NMR. So we are not going to consider these 4 as non-equivalent. We're going to consider them as all equivalent protons, because we are not going to have a chiral deuterated solvent to do our analysis in. Alright, so that said, you said, well, what about these? Could we have had enantiotopic relationships within these 6? I hope you're saying no. I take any one of these 6 and replace it with xenon, and you don't create a chirality center. So it's special when you have typically a CH2 group, where if you replace one of those H's, you get a chirality center. Those 2 protons are enantiotopic. Well, let's move on. How many signals then do we expect to see in the proton NMR for this diethyl ether? Well, then we'd expect just 2, because these 4 we just said without the chiral solvent are equivalent, and these 6 of course were equivalent. So we'd expect 2 signals, and kind of thinking ahead, we'd expect the area for one signal to be I guess 2/3 that of the other. So this would be 2/3 the height or area that the signal representing these 6 would be. Kind of jumping, looking a little bit ahead. Let's move on to some more difficult structures and proposing the number of signals. So we need to find the number of expected signals. That's always our first step when we move from structure to spectra. Having the structure, how do we propose spectra? We find the number of expected signals. So let's take this structure, 2-methyl-1-butene. We'll look at it and see how many non-equivalent protons there are for 2-methyl-1-butene. So we can start looking at these two from the left and coming to the right. This sits across from a methyl, and this sits across from an ethyl. Very, very similar, and they may have very, very similar signals, but we cannot say they're truly equivalent. If it was, it's just by coincidence if they're magnetically equivalent or having the same ppm signal, but chemically they are not equivalent, these two, so we can say that's 1, that's 2. Now, of course, this carbon has no protons off of it, so we move out to this carbon and to this carbon. We can certainly distinguish these 3 protons from any others within 2-methyl-1-butene. They don't look like these two. They're off carbon that's next to a double bond. These were off of a double bond. They are on a position next to the double bond. These are 2 steps away, 1, 2. So these two are not equivalent. That's pretty obvious. We can discern this methyl group from this methyl group. So there's our 3rd, and of course our 4th and our 5th. So we could say that would be a total possible number of signals of 5. It may just be 4 because these are very similar, but there would be the maximum number of signals in the spectra for this structure of 5. So I get my fingers up there, 5. So 5 signals. So that's how we can look at a structure and find the number of expected signals, or, in other words, the number of non-equivalent protons. Now let's look at position for protons. So we kind of covered a little bit of how you go about looking at a structure to determine non-equivalent protons. So we have to, again, putting in our little notes on what to do if we need to predict NMR from structure, is find number of expected signals. That's the first thing we have to do if we're given a structure for which we have to predict NMR. The second is arrange expected signals from most shielded to least shielded. Most shielded was down here. Most deshielded was here. This was our downfield side. We said in the first video that deshielded goes with the downfield, and this was the upfield side. So there are 5 regions that you should know for NMR spectra of organic molecules, proton NMR spectra. You should know 5. 1, the alkyl range, where the proton that's generating the signal is connected to an sp3 carbon that's connected to other sp3 carbons. So we call that an alkyl proton, and it's really from the 0.5 to 1.5 range. Let's go 0.5 to 1.5. Kind of that range there. You should know that one. That's one. And we're going to jump from there to what's called the allylic or benzylic, where we're on an sp3 carbon, this proton that's giving the signal, but it's not next to an sp3 carbon all the way around. It has an sp2 carbon bonded to it. So this had all sp3s everywhere. This proton's on a carbon that's connected to other carbons that are sp3 hybridized. This one's on an sp3 carbon, but it's connected to an sp2 carbon. That's called an allylic or benzylic, and so that's a 2.5 to 1.5 range, roughly. These are just general proximities of where they fall in the spectra. 2.5 to 1.5, and these we'll call allylic. Allylic, and that's going to be on the next page here, so I'm not going to worry about writing it down. Allylic. The next one we're going to say heteroatom affected. Affected not being that they're directly bonded to a heteroatom, an oxygen, a halogen, nitrogen, but they're on a carbon that's sp3, and that carbon's bonded to a heteroatom. So sp3 carbons that the proton's on, but that carbon is bonded to an O, an X, or an N. That's going to be in the 4.5 to to 2.5 range ppm. So we've got 3 knocked out right there. We've got alkyl, proton on a carbon that's sp3 that's bonded to sp3 carbons, allylic or benzylic. Next, on a carbon that's sp3 that's bonded to a sp2 carbon in a benzene ring or just in a double bond. The heteroatom affected ones, where we're on a carbon that's sp3 that's bonded to a heteroatom. And this one's vinylic, meaning it's a proton first time that's actually bonded to an sp2 carbon. Not on an sp3 like we've seen in the last 3, but on an sp2 carbon. It kind of shifts pretty far downfield. We get a 6.5 to 4.5 range typically for those types of protons. And then we also have our protons, this is it, that we're going to consider. That's not on an sp2 carbon that's just in a double bond, but it's on an sp2 carbon that's in a benzene ring, so, or in an aryl ring, but so we should be saying aryl protons. Typically benzene, but other aromatic systems, if a proton's connected to the ring, that's aromatic. We call that an aryl type of proton. It usually falls in the 8.5 to 6.5 ppm range. So know those 5, and let's use those 5 as we close this video and look at an example problem. So we have to find the number of expected signals. Remember, that was the first thing to do. Arrange expected signals. And right now we're not going to look at the drawing of the peak. We're just going to show arrows as to where they fall, the signals that we're starting to think about for a given structure. So let's take this example problem, and this one has some chirality, so there's some complexity to this one that we're not going to touch on. But let's just find the number of expected signals, or follow at least the numbers that are here. Now this oxygen in this ring gives us some anisotropic character or asymmetric character. We know if there had been a carbon here, then these two branches would be the same. They would look the same. But the O is like our reference point. I can say I'm a proton on a carbon across from the oxygen, and there is nobody else like that. This is unique from 2, 4, 5, and 6 because it's on a proton on a carbon that's across in the 6-membered ring from the oxygen. So that's certainly unique. 2 is 2 steps away from that oxygen, but not having a vinyl group off of it. So 2 and 4 are both 2 steps away, but we could certainly pick 2 and never mistakenly, if it was thrown over the wall and then thrown back, pick 4 instead of 2. So 2 is a unique position, and the protons off of 2 would be unique. And then 3, I'm just kind of jumping around, and we'll talk about the order as to why we did this. 3 is certainly unique, a methyl group. There is no other methyl group, a CH3 group, in this structure. 4 has a CH group, just 1 hydrogen off of this carbon, so that's unique. And then, of course, 5 and 6 may be similar, but 5 is on the side of this ring that has the oxygen, that has this branch off of it, and 6 does not. And then, of course, 7 and 8 differ because this orientation of the 2 hydrogens, if we draw them in, would be locked in by the double bond. This proton being on the side that has the 6-membered ring, this proton being on the side that has the methyl group. So there are 7 and 8. Now, I'm not going to touch on the fact that we really have, I guess, chirality here with this carbon being a chirality center, that these protons in it 1, 2, 6, and 5 would be diastereotopic to each other, meaning what they see from this carbon looking back to this group, this has to be on the wedge or dash, would be different depending upon where they're oriented. I'm not going to get into that. Just going to say let's treat those as falling fairly close to each other as far as a signal, and not consider this chirality or this additional source of splitting of the signals, so that these 2 protons really aren't equivalent. So let's not consider that additional cause for a number of signals to go up for this structure. So we can say the protons at positions 1 and 2 would be upfield because they're on carbons that are sp3 that are next to carbons that are sp3. So these would be our alkyl And I know again that there would really be 4 signals considering the stereochemistry, but they would fall in that 1.5 to 0.5 range. Probably a little bit above 1, because typically just the methyl groups go below 1. Now let's look at 3. 3 is an allylic. It's a proton on an sp3 carbon that's bonded to an sp2, so it makes it into this range we said, 1.5 to 2.5, this allylic, or benzylic next to a benzene ring. And that's true for both 3 and for 4. 3 and 4 would fall in that range. 5 and 6 are heteroatom affected protons, and again we have 4 signals because 5 and 6 we have 2 protons that see this chirality from different sides, but it would still be heteroatom affected. I'll just put hetero. And then lastly 7 and 8 are right off of this double bond, so they'd be vinylic. That's how we can start. Now I didn't show the peaks. I'm just moving at this thing slowly and saying we're going to have signals falling at these points within the NMR spectra. In the next video we'll close the deal. We'll look at a structure and ask all the questions that are needed to be asked to draw the full spectra. This just gives us an idea of how we can go about that process. Find the number of signals that you have given the structure, look for non-equivalent protons, and then arrange those signals by those 5 classifications: alkyl, allylic, heteroatom affected, vinylic, and aryl. We did not have any of those protons. Bye-bye.